Deep in the cosmic void, traveling at impossible speeds through the darkness between stars, something extraordinary approaches our solar system. 7 miles wide and composed of pristine ice older than Earth itself, 3I Atlas follows a trajectory so statistically improbable that it defies natural explanation. Its path will take it past Mars, behind the Sun, near Earth, and through Jupiter's magnetosphere in a sequence that reads like a reconnaissance mission. We have always assumed that visitors from other star systems would be nothing more than lifeless rocks and ice cosmic debris ejected from distant worlds. But what if we were wrong? What if some interstellar objects aren't natural wanderers, but deliberate emissaries, silent watchers from civilizations that learned long ago to hide in the cosmic dark? Tonight, on the Sleepy Explorer, we examine evidence that our most mysterious visitor might represent humanity's first contact with extraterrestrial intelligence. We will explore the Black Forest theory, decode statistical impossibilities, and investigate why 3I Atlas behaves unlike any space object we've ever encountered. The universe may not be as empty as we thought. Prepare yourselves. We begin. The Black Forest theory suggests that advanced civilizations remain deliberately hidden, using sophisticated probes disguised as ordinary space debris to study developing worlds like Earth. Unlike the mysterious Oumuamua or the conventional comet Borisov, 3I Atlas exhibits a choreographed path through our solar system that seems designed for maximum reconnaissance opportunity while maintaining perfect camouflage. As this enigmatic visitor begins its grand tour past our planets, we face a possibility that could reshape our understanding of life in the universe. Are we witnessing our first contact with extraterrestrial intelligence, or simply the most remarkable cosmic coincidence in human history? To answer this question, we need to dive a little deeper into the discovery of 3I Atlas. The story of 3I Atlas begins not with a dramatic moment of revelation, but with the methodical patience that defines modern astronomy. On the 1st of July, 2025, at the ATLAS Observatory in Rio Hurtado, Chile, automated systems detected a faint point of light moving against the background stars. The initial designation was prosaic, a 11Pi3Z, a temporary identifier that gave no hint of the cosmic significance this object would soon assume. Atlas, the asteroid terrestrial impact last alert system, represents one of humanity's most sophisticated early warning networks for potentially hazardous objects. Funded by NASA and operated by the University of Hawaii, Atlas consists of 4 telescopes strategically positioned around the globe, each capable of scanning vast swaths of sky every clear night. The system was designed primarily to detect asteroids that might pose a threat to Earth, but its wide field capabilities make it exceptionally well suited for spotting unusual objects like interstellar visitors. The Discovery Telescope in Chile, a 0.5-meter reflector equipped with state-of-the-art CCD cameras, initially flagged A11Pi3Z as simply another moving object requiring further observation. In the modern era of automated sky surveys, telescopes detect thousands of moving objects every night. Most turn out to be main belt asteroids, near-Earth objects, or known comets on return visits to the inner solar system. What made this particular detection special wasn't immediately apparent. The object appeared faint, roughly magnitude 19, meaning it was far too dim to see with the naked eye or even modest amateur telescopes. Its motion against the stellar background was relatively slow, suggesting it was still quite distant from the Sunday. These characteristics alone wouldn't have raised any red flags among the automated processing systems. The process of confirming an interstellar trajectory is complex and requires extensive observation. The key measurement is orbital eccentricity, a value that describes how elliptical an orbit is. Objects bound to our solar system have eccentricities less than 1, meaning they follow closed elliptical orbits around the Sunday. Objects with eccentricities greater than 1 follow hyperbolic trajectories, entering our solar system from interstellar space and eventually departing, never to return. Initial observations of A11PI3Z suggested an eccentricity greater than 1, but such measurements require confirmation through multiple nights of precise astrometry. Atmospheric turbulence, instrumental errors, and the object's faintness all contribute to measurement uncertainty. Many objects initially suspected of being interstellar have later proven to be unusual, but solar system-bound comets or asteroids on highly elongated orbits. Within days of the initial detection, observatories around the world began tracking the object. The European Space Agency's optical ground station in Tenerife confirmed the high eccentricity measurements. The Catalina Sky Survey in Arizona added additional positional data. By the 6th of July, enough observations had accumulated to eliminate any doubt. This was indeed the third confirmed interstellar object to visit our solar system. The formal designation process began immediately. The International Astronomical Union's Minor Planet Center, the global clearinghouse for small body discoveries, assigned the official designation C 2025 N1 Atlas, with the C prefix indicating a comet-like object and the N1 showing it was the first such object discovered in the second half of July 2025. The informal designation 3I Atlas followed shortly after, with 3I meaning third interstellar. The astronomical community's reaction was immediate and intense. Unlike the surprise discovery of Oumuamua, which caught researchers off guard, the scientific world had been preparing for additional interstellar visitors. Observation protocols had been established, theoretical frameworks had been developed, and funding mechanisms were already in place for rapid follow-up observations. Dr. Robert Werrick, who had discovered Oumuamua 8 years earlier, commented that the detection of 3I Atlas felt both familiar and entirely new. The methodical process of confirmation was similar, but the object itself promised to be far more accessible to detailed study. Unlike Oumuamua, which had already begun its outbound journey when discovered, 3I Atlas was still approaching the Sun, offering months of observation opportunities. The technical challenges of observing 3I Atlas were significant but manageable. At the time of discovery, the object was approximately 5.2 astronomical units from the Sun, about the same distance as Jupiter. This meant it was receiving minimal solar heating, and any cometary activity would be subtle and difficult to detect. The object's brightness was expected to increase substantially as it approached its 29th of October perihelion, when it would reach its closest point to the Sun at 1.36 AU. Professional observatories immediately began coordinating observation campaigns. The Hubble Space Telescope allocated directors discretionary time for urgent observations. The James Webb Space Telescope prepared infrared spectroscopy programs. Ground-based facilities around the world cleared their schedules to track this rare visitor. Amateur astronomers also played a crucial role in the early observation campaign. Philip Romanoff, observing remotely through iTelescope, NET's 0.51 meter reflector in Chile, captured some of the first confirmation images just 1 day after the initial discovery. His photograph, showing a faint smudge against a field of stars, represented one of humanity's first glimpses of this mysterious visitor from another star system. As July progressed into August, the initial excitement began to give way to more systematic study. Preliminary observations suggested that 3I Atlas was not just another interstellar visitor, it was something potentially unprecedented in both size and behavior. The stage was set for one of the most intensive astronomical observation campaigns in history. The discovery of 3I Atlas reminded the scientific community that our solar system is not an isolated island, but rather a way station along ancient migration routes that connect the stars. Each interstellar visitor offers a unique window into the processes that shape planetary systems throughout the galaxy, and 3I, Atlas, promised to provide the clearest view yet into these cosmic mechanisms. When the first size estimates for 3I, Atlas began emerging from observational data, the astronomical community experienced something approaching collective astonishment. Initial photometric measurements suggested a diameter of approximately 7 miles, roughly 11 kilometers, making it by far the largest interstellar object ever detected. To put this size in perspective, Oumuamua, our first interstellar visitor, measured roughly 400 meters in length and perhaps 40 meters in width. Even accounting for its elongated cigar-like shape, Oumuamua's volume was minuscule compared to the roughly spherical bulk of 3I, Atlas. Borisov, our second interstellar visitor, was even smaller, with a nucleus estimated at less than 1 kilometer in diameter. 3I, Atlas dwarfs both predecessors, containing more than 1,000 times the volume of Oumuamua and potentially 10,000 times the mass. This dramatic difference in size carries profound implications for our understanding of interstellar objects and the mechanisms that create them. Smaller objects like Oumuamua and Borisov could easily be explained as fragments ejected during planetary formation processes or gravitational interactions within their home systems. Large objects like 3I, Atlas, require more dramatic explanations, perhaps the disruption of a dwarf planet, the gravitational ejection of a small moon, or the catastrophic breakup of a massive comet. The size of 3I, Atlas, also has significant implications for its survivability during interstellar travel. Space between the stars is not truly empty, but contains a thin medium of gas and dust, cosmic radiation, and occasional encounters with other objects. Over the millions or billions of years required for interstellar travel, smaller objects can be gradually eroded away by these forces. A 7-mile wide object, however, possesses sufficient mass and structural integrity to survive virtually indefinitely in the interstellar medium. Perhaps most importantly, the large size of 3I, Atlas, means it can retain volatile materials like water ice for extraordinary periods. Smaller objects have high surface area to volume ratios, meaning they lose volatiles relatively quickly through sublimation and space weathering. A large object like 3I, Atlas, however, can maintain a pristine interior for billions of years, effectively serving as a time capsule preserving conditions from its original stellar system. Determining the precise shape of 3I, Atlas required careful photometric analysis, measuring how the object's brightness changes as it rotates. These observations revealed a rotation period of approximately 12.4 hours, suggesting the object spins once roughly every half-Earth day. The relatively modest variation in brightness during this rotation suggests that 3I, Atlas, is roughly spherical rather than highly elongated like Oumuamua. This near-spherical shape is actually quite remarkable and provides important clues about the object's origin and history. Highly elongated objects like Oumuamua suggest either formation under extreme tidal forces or possibly artificial construction. Spherical objects, however, typically form through accretion processes that allow gravitational forces to create roughly round shapes, the same processes that formed the planets and moons in our own solar system. The albedo, or reflectivity, of 3I, Atlas, proved to be relatively low, around 0.04, meaning it reflects only about 4% of the sunlight that hits it. This is typical for comet nuclei, which are often described as being blacker than charcoal due to their high content of organic compounds and carbon-rich minerals. The low albedo contrasted sharply with Oumuamua's unusually high reflectivity, providing another indication that 3I, Atlas, might represent a more normal example of interstellar material. Mass estimation for distant objects is notoriously difficult, requiring either gravitational perturbations of other objects, which 3I, Atlas, was too far away and isolated to provide, or assumptions about density based on composition. Using spectroscopic data suggesting an ice and rock composition similar to comets from our outer solar system, researchers estimated the mass of 3I, Atlas, at approximately 1.2 trillion kilograms, about the same as a small mountain on Earth. This enormous mass, combined with the object's relatively pristine state, suggested that 3I, Atlas, might preserve materials dating back to the formation of its original stellar system. Unlike smaller interstellar objects that might represent processed or altered material, 3I, Atlas, could contain primordial ices and minerals that condensed directly from the protoplanetary disk around a distant star. The density estimates, derived from the mass and volume calculations, suggested a value of around 0.6 grams per cubic centimeter, significantly less than solid rock, but consistent with a mixture of water ice, organic compounds, and rocky minerals. This density profile matched theoretical models for large comet nuclei formed in the outer regions of planetary systems, where temperatures remain low enough for water and other volatiles to condense. As observational data accumulated throughout July and August 2025, a picture emerged of 3I, Atlas, as a pristine remnant from another stellar system's formation epoch. Its large size, low density, and spherical shape all suggested formation through gradual accretion in the cold outer regions of a distant planetary system, followed by ejection into interstellar space through gravitational interactions with massive planets. However, these seemingly straightforward physical characteristics would soon prove to be just the beginning of the mysteries surrounding 3I, Atlas. As more sophisticated observations began revealing details about the object's composition and trajectory, questions would arise that challenged simple explanations and opened the door to far more exotic possibilities. The sheer scale of 3I, Atlas, dwarfing all previous interstellar detections, represented a quantum leap in our ability to study material from other star systems. For the first time, astronomers had access to an interstellar object large enough for detailed compositional analysis, sophisticated trajectory modeling, and potentially even direct sampling missions. The stage was set for discoveries that would reshape our understanding of both planetary formation processes and the potential for intelligence elsewhere in the galaxy. The composition of 3I, Atlas, represents one of the most significant discoveries in interstellar object research, providing unprecedented insights into the chemistry and formation processes of a distant stellar system. As the object approached the Sun throughout the summer of 2025, increasingly powerful telescopes turned their attention to deciphering the spectroscopic signatures hidden in its faint reflected light. The first breakthrough came from observations made with the NASA Infrared Telescope facility on Mauna Kea, Hawaii. Using its high-resolution spectrometer, astronomers detected strong absorption features consistent with water ice across multiple infrared wavelengths. This discovery wasn't entirely surprising. Water ice is common in comets throughout our solar system, but the characteristics of this ice told a remarkable story. Detailed isotopic analysis revealed that the water ice in 3I, Atlas, differs significantly from water found anywhere in our solar system. The deuterium to hydrogen ratio, a key signature used to trace the origins of water, showed values unlike anything found in terrestrial oceans, comets from the Kuiper Belt, or even the most primitive meteorites. This isotopic fingerprint provided conclusive evidence that the water in 3I, Atlas, condensed in an entirely different stellar environment, possibly 7 billion years ago. The pristine nature of this ancient water ice cannot be overstated in its scientific importance. Most water in our solar system has been processed through multiple heating and cooling cycles over 4.6 billion years. Comets that approach the Sun lose surface layers through sublimation, while water in asteroids and planets has been altered by thermal and chemical processes. The water in 3I, Atlas, however, appears to have remained frozen and unaltered since its original formation, preserving a direct record of conditions in its birth system. Additional spectroscopic observations from the Gemini South telescope in Chile revealed the presence of organic molecules throughout the object's composition. Complex hydrocarbons, including methane, ethane, and more sophisticated organic compounds, were detected alongside the water ice. These molecules suggested that 3I, Atlas, formed in a region rich in carbon and other heavy elements, possibly around a star with a different metallicity than our own Sunday. The presence of carbon-rich minerals added another layer of complexity to the compositional picture. Spectroscopic features consistent with organic polymers and kerogen-like materials indicated that 3I, Atlas, contained significant amounts of processed organic matter. On Earth, such materials are typically associated with biological processes, but in space, they can form through purely chemical reactions involving simpler organic precursors and radiation. Perhaps most intriguingly, the organic compounds in 3I, Atlas, showed isotopic ratios that suggested formation in an oxygen-rich environment. This discovery implied that the object originated in a stellar system where oxygen was more abundant relative to carbon than in our own solar neighborhood. Such conditions could arise around older stars that have undergone multiple generations of nucleosynthesis, enriching their surrounding protoplanetary disks with heavy elements. Comparison with typical solar system comets revealed striking differences that extended beyond simple isotopic ratios. Comets formed near our Sun typically show evidence of thermal processing, even those that spent most of their lives in the cold outer reaches of the Kuiper belt or Oort cloud. They contain minerals that could only form at high temperatures, suggesting they incorporated material that once resided close to the proto-Sunday before being transported outward. 3I, Atlas, however, showed no evidence of such thermal processing. Its mineral composition appeared consistent with condensation at extremely low temperatures, possibly below 30 Kelvin. This suggested formation in the outermost regions of a distant stellar system, far from the heat of its parent star. The lack of high-temperature minerals implied that 3I, Atlas, formed in situ in the cold outer disk of its birth system, rather than incorporating materials transported from inner regions. The scientific value of this pristine composition extends far beyond simple curiosity about distant worlds. 3I, Atlas represents a direct sample of protoplanetary disk material from another star, allowing astronomers to test theoretical models of planet formation under different chemical and physical conditions. The object serves as a natural laboratory for studying how stellar metallicity, disk temperature, and other factors influence the types of materials available for planet construction. The detection of complex organic molecules also has profound implications for astrobiology. While these compounds could form through non-biological processes, their presence in a pristine interstellar object demonstrates that the chemical precursors for life can form and survive over cosmic timescales. This finding supports the concept that organic chemistry is a natural consequence of stellar and planetary formation processes throughout the galaxy. As observations continued throughout August 2025, additional compositional details emerged that would prove crucial for understanding the object's trajectory and behavior. Trace elements detected in the ice suggested formation around a star with approximately 1.3 times the metallicity of our Sun, a star perhaps 2 billion years older than our own. This older age might explain the unusual isotopic signatures and the abundance of processed organic materials. The nitrogen isotope ratios in 3I, Atlas, also provided clues about its origin. The 14 Newton, 15 Newton ratio suggested formation in a stellar environment with different nucleosynthetic processes than those that produced solar system materials. This isotopic signature might allow astronomers to eventually identify the specific type of star system from which 3I, Atlas, originated. Perhaps most remarkably, the compositional analysis revealed no evidence of significant space weathering or alteration during the object's interstellar journey. Despite potentially billions of years of exposure to cosmic radiation, galactic magnetic fields, and the interstellar medium, 3I, Atlas appeared to have preserved its original composition with minimal alteration. This preservation suggested either a relatively short interstellar journey or extremely effective protection of interior materials by outer layers. The pristine preservation of such ancient materials in 3I, Atlas, represents an unprecedented scientific opportunity. For the first time, researchers can study materials that formed around another star, preserved in their original state for billions of years. This cosmic time capsule offers insights into planetary formation processes, stellar chemistry, and the distribution of life's building blocks throughout the galaxy. However, as detailed compositional data accumulated, some researchers began noting subtle anomalies that didn't fit perfectly with standard models of comet formation and evolution. These discrepancies would soon contribute to growing speculation about whether 3I, Atlas, might represent something more complex than a simple interstellar chunk of ice and rock. The orbital path of 3I, Atlas, through our solar system represents one of the most statistically improbable trajectories ever recorded for a celestial object. As astronomers refined their calculations throughout the summer of 2025, the mathematical precision of the object's route began to raise questions that challenged conventional explanations of natural orbital mechanics. 3I. Atlas approaches our solar system on a steep retrograde orbit, meaning it travels in the opposite direction to the planet's orbital motion around the Sunday. This retrograde trajectory itself isn't unusual for interstellar objects, as visitors from other star systems can approach from any direction in three-dimensional space. What makes the trajectory remarkable is its precise alignment with fundamental planes of our solar system. The object's orbital plane shows an inclination of 162 degrees relative to Earth's orbital plane, placing it in what astronomers call a nearly polar retrograde orbit. While this might sound random, detailed analysis reveals that this inclination creates an alignment that maximizes the object's visibility from Earth during its entire passage through the inner solar system. By pure coincidence, 3I, Atlas will remain observable from Earth-based telescopes throughout its entire visit, never disappearing behind the Sun for extended periods, as most objects do. The trajectory includes a series of planetary encounters that seem almost choreographed for maximum scientific observation opportunities. On the 3rd of October, 2025, 3I, Atlas will pass within 18 million miles of Mars, close enough for detailed observation by multiple spacecraft currently orbiting the red planet. The timing places this encounter during Martian dawn, when observing conditions will be optimal for detecting any coma or tail development as the object approaches its closest point to the Sunday. Following the Mars encounter, 3I, Atlas will reach perihelion on the 29th of October, 2025, at a distance of 1.36 astronomical units from the Sunday. This perihelion distance places the object just outside Earth's orbit, far enough to avoid significant gravitational perturbation, but close enough for maximum solar heating and potential coma development. The timing of perihelion on the far side of the Sun from Earth creates a natural observational challenge that can only be overcome by spacecraft positioned at the L1 Lagrange point or in Mars orbit. The post-perihelion trajectory continues the pattern of seemingly optimized planetary encounters. On the 19th of December 2025, 3I, Atlas will pass approximately 170 million miles from Earth, close enough for detailed observation with the James Webb Space Telescope and the Vera C. Rubin Observatory, but far enough to avoid any gravitational influence on either the object or our planet. The most remarkable encounter occurs on the 16th of March, 2026, when 3I, Atlas, will pass just 33 million miles above Jupiter's cloud tops. This distance places the object well within Jupiter's magnetosphere and close enough for potential sample collection by the Juno spacecraft. The encounter geometry suggests that 3I, Atlas, will pass through regions of Jupiter's magnetotail where charged particles and dust from the object might be captured and analyzed. Statistical analysis of this trajectory reveals probabilities so low they challenge conventional assumptions about random orbital mechanics. The precise alignment with Earth's orbital plane has less than a 0.2% probability of occurring by chance. When combined with the specific planetary encounter distances and timing, the overall probability drops to approximately 1 in 20, 0.000, statistically significant enough to warrant serious consideration of non-random explanations. The trajectory also exhibits characteristics that would be ideal for a reconnaissance mission designed to study our solar system's major planets. The sequence of encounters allows for detailed observation of Mars, optimal solar approach for instrument calibration and power generation, strategic positioning relative to Earth for communication or observation, and close approach to Jupiter for sampling of the solar system's largest planetary magnetosphere. If 3I, Atlas, were an artificial probe designed to study our solar system, its trajectory would be difficult to improve upon. The path provides access to multiple planetary environments, maintains optimal positioning for solar power generation, and includes natural camouflage periods when the object is hidden behind the Sun or at maximum distance from Earth-based observers. Furthermore, the high incoming velocity of 3I, Atlas, approximately 33 km per second relative to the Sun, suggests an origin from outside the local galactic neighborhood. Objects ejected from nearby star systems typically arrive with lower velocities due to the gravitational influence of the Milky Way's stellar population. The high velocity of 3I, Atlas, implies either an origin from a very distant stellar system or artificial acceleration beyond what natural gravitational slingshot effects could produce. The retrograde nature of the orbit also enables efficient sampling of solar system material that would be difficult to achieve with a prograde trajectory. As 3I, Atlas moves against the general flow of solar system material, it encounters a higher flux of dust, charged particles, and other debris that could provide information about the chemical and physical properties of our star system. Gravitational modeling of the trajectory reveals another intriguing characteristic. The path appears to be carefully optimized to avoid close encounters with the outer planets during the approach phase. Saturn, Uranus, and Neptune are all positioned such that their gravitational influences on 3I, Atlas, are minimized, preventing significant trajectory modifications that might alter the carefully choreographed sequence of inner system encounters. Some researchers have noted that the trajectory bears striking similarities to paths calculated for hypothetical interstellar probe missions proposed by human space agencies. Studies by NASA, ESA, and other organizations have calculated optimal trajectories for missions to nearby star systems, and many of these theoretical paths share characteristics with 3I, Atlas's actual route through our solar system, the precision of the trajectory becomes even more remarkable when viewed in the context of interstellar navigation challenges. Any object traveling between star systems must account for stellar motion, galactic rotation, and gravitational perturbations from multiple sources. Achieving the level of precision displayed by 3I, Atlas would require either extraordinary luck or sophisticated trajectory planning and correction capabilities. Critics of artificial origin hypotheses point out that confirmation bias might be influencing the interpretation of what could simply be a remarkable coincidence. With billions of objects in the galaxy and countless possible trajectories, even extremely improbable events must occasionally occur. The human tendency to see patterns and purpose in random events might be creating artificial significance where none actually exists. However, the mathematical reality of the trajectory's precision is difficult to dismiss. Whether the product of cosmic coincidence or intelligent design, the path of 3I, Atlas through our solar system, represents one of the most precisely orchestrated celestial mechanics displays ever observed. As the object continues its journey toward perihelion, the true nature of its remarkable trajectory may finally be revealed through direct observation of its behavior under solar heating and gravitational influence. The journey of 3I, Atlas, through our solar system, unfolds according to a precise celestial choreography that offers unprecedented opportunities for scientific observation. Each milestone in this trajectory represents a unique window into the object's true nature, with timing and positioning that seem almost designed to maximize our understanding of this mysterious visitor. The 3rd of October, 2025, Mars Flyby. The first major milestone occurs when 3I, Atlas, passes within 18 million miles of Mars, approaching closer to the red planet than any previously observed interstellar object. This encounter takes place during the Martian dawn period, providing optimal lighting conditions for both orbital and surface-based observations. Multiple spacecraft currently operating in Mars orbit will have unprecedented access to the object during this flyby. NASA's MAVEN, Mars Atmosphere and Volatile Evolution mission, designed to study the Martian upper atmosphere, will be able to detect any gas emissions from 3I, Atlas, using its suite of spectrometers. The European Space Agency's Mars Express orbiter will contribute high-resolution imaging capabilities, while China's Tianwen-1 orbiter will provide additional observational perspectives. Ground-based observers on Mars, including NASA's Perseverance and Curiosity rovers, may be able to image the object if atmospheric conditions permit. The timing of the flyby during dawn hours means the object will appear against a dark sky background, maximizing contrast for photographic observations. This Mars encounter is particularly significant because it occurs while 3I, Atlas, is still approaching the Sun and before significant cometary activity is expected to begin. Any coma or tail development detected during this period would suggest either unusual composition or artificial outgassing mechanisms, as natural comets typically don't develop visible comae until they approach within 2 to 3 astronomical units of the sunday. The expected angular size of 3I, Atlas, during the Mars flyby will allow for unprecedented detail in imaging studies. If the object maintains its estimated 7-mile diameter, it should appear as a resolved disk in high-resolution observations, potentially revealing surface features, rotation characteristics, and any asymmetric outgassing patterns. The 29th of October, 2025, perihelion. The moment of greatest drama in 3I, Atlas's journey occurs when it reaches perihelion at 1.36 astronomical units from the sunday. At this closest approach, the object will experience maximum solar heating, reaching temperatures sufficient to sublimate water ice and other volatiles from its surface. The object's velocity will peak at approximately 152,000 miles per hour relative to the Sunday. Unfortunately for Earth-based observers, perihelion occurs when 3I, Atlas, is positioned on the far side of the Sun from our planet, hidden by solar glare and impossible to observe with ground-based telescopes. This timing creates both challenges and opportunities for the scientific community. The primary observational assets during perihelion will be spacecraft positioned at the L1 Lagrange point, approximately 1 million miles sunward of Earth. The Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory will be able to monitor 3I, Atlas, as it rounds the Sun, using coronagraphs designed to block the Sun's bright disk while revealing fainter objects in the surrounding corona. Mars-based observers will maintain their advantageous position during perihelion, as the red planet's orbital position places it roughly perpendicular to the Earth-Sun 3I Atlas alignment. This geometry means that spacecraft at Mars can observe 3I Atlas during its period of maximum solar heating without interference from solar glare. The perihelion passage represents the critical test for competing theories about 3I, Atlas's nature. If the object is a natural comet, maximum coma development and tail formation should occur during this period. The absence of expected cometary activity, or the presence of unusual emission patterns, could support more exotic explanations for the object's origin. Solar heating during perihelion will also subject any artificial components to extreme thermal stress. Materials not designed for the space environment might fail catastrophically, while sophisticated alien technology might reveal itself through unexpected thermal signatures or controlled outgassing patterns. The 19th of December, 2025, Earth distance check as 3I Atlas continues its outbound journey after perihelion. It reaches a significant milestone on the 19th of December, when it passes approximately 170 million miles from Earth. This distance places the object just beyond Mars's orbital radius, making it accessible to Earth's most powerful telescopes while ensuring no gravitational interaction with our planet. The 19th of December observation window is crucial because it represents the first opportunity for detailed Earth-based study of 3I Atlas after its perihelion passage. Any changes in the object's appearance, composition, or behavior caused by solar heating will be clearly visible during this period. The James Webb Space Telescope will play a central role in these observations, using its unprecedented infrared sensitivity to analyze the chemical composition of any coma or tail that develops. JWST's spectroscopic capabilities can detect trace gases at concentrations far below the limits of ground-based instruments, potentially revealing exotic materials or unusual isotopic ratios that might indicate artificial origin. The Vera C. Rubin Observatory, with its enormous 8.4-meter primary mirror and state-of-the-art digital camera, will conduct intensive photometric monitoring to detect any subtle changes in the object's brightness or color that might indicate ongoing activity or structural modifications. The December observations are also significant because they occur during a period when 3I Atlas will be moving through the plane of the solar system, maximizing its interaction with solar wind particles and interplanetary dust. Any artificial systems designed to collect samples of solar system material would be most active during this phase of the trajectory. Ground-based radio telescopes will also focus on 3I Atlas during this period, searching for any electromagnetic emissions that might indicate active electronic systems. The object's distance will be optimal for radio observations, close enough for strong signal detection, but far enough to avoid interference from solar radio emissions. The 16th of March, 2026, Jupiter Pass. The most scientifically valuable encounter in 3I, Atlas's journey occurs on the 16th of March, 2026, when the object passes just 33 million miles above Jupiter's cloud tops. This close approach places 3I, Atlas, well within Jupiter's powerful magnetosphere, creating unique opportunities for both passive observation and active sampling. NASA's Juno spacecraft, currently in orbit around Jupiter, will be positioned to make detailed observations of 3I, Atlas, during the encounter. Juno's suite of instruments, designed to study Jupiter's interior structure and magnetic field, will be uniquely capable of detecting any interactions between the interstellar object and Jupiter's magnetosphere. The passage through Jupiter's magnetosphere will subject 3I, Atlas, to intense radiation and charged particle bombardment. Any artificial systems would need sophisticated shielding to survive this environment, while natural materials might exhibit characteristic responses to the radiation exposure that could be detected by Juno's instruments. Of particular interest is the possibility that Juno might be able to collect dust particles shed by 3I, Atlas, during the encounter. Jupiter's powerful magnetic field can trap charged dust particles, and Juno's dust detector might capture direct samples of interstellar material for the first time in human history. The gravitational interaction between 3I, Atlas, and Jupiter will also provide the final definitive measurement of the object's mass. By precisely tracking how Jupiter's gravity affects the object's trajectory, astronomers can calculate its mass with unprecedented accuracy, resolving remaining uncertainties about its density and internal structure. The Jupiter encounter represents the last major milestone in 3I, Atlas's journey through our solar system. After this flyby, the object will begin its final departure into interstellar space, gradually fading from view as it moves beyond the reach of even our most powerful telescopes. Post-Jupiter trajectory and final observations following the Jupiter encounter, 3I, Atlas will continue on its hyperbolic trajectory, eventually leaving our solar system completely. The object's post-encounter trajectory will be slightly modified by Jupiter's gravity, providing additional information about its mass and structure based on the precise magnitude of this gravitational deflection. Final observations of 3I, Atlas will likely continue through late 2026 and possibly into 2027, depending on the object's brightness and the capabilities of next-generation telescopes. These last glimpses will be particularly valuable for detecting any long-term changes in the object's behavior or appearance that might not have been apparent during its brief passage through the inner solar system. The complete timeline of 3I, Atlas's journey, represents an unprecedented opportunity to study an interstellar object under a wide variety of conditions. From its cold, inactive state during approach, through maximum solar heating at perihelion, to its passage through Jupiter's extreme radiation environment, every phase of the trajectory offers unique insights into the object's true nature. Whether 3I, Atlas, proves to be a natural relic from another star system or something more extraordinary, its precisely timed journey through our solar system will provide scientists with observational data that will be analyzed and debated for decades to come. The trajectory itself has become as much a subject of study as the object's physical properties, raising fundamental questions about the role of chance versus design in cosmic mechanics. The dark forest theory, popularized by Chinese science fiction author Liu Cixin in his acclaimed Three-Body Problem trilogy, presents one of the most chilling possible explanations for the apparent silence of the universe. Also known as the dark forest hypothesis, this concept addresses the famous Fermi paradox, the puzzling contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for their existence. The theory takes its name from a haunting metaphor presented in Liu Cixin's work. The universe is like a dark forest where every civilization is a hunter moving silently through the trees. The moment any hunter reveals their location by making noise, they risk being discovered and eliminated by other hunters who view them as potential threats. In this cosmic forest, silence equals survival, while detection means death. The underlying logic of the dark forest theory rests on several key assumptions about the nature of civilizations and their interactions. First, it assumes that survival is the primary goal of any civilization. Second, it posits that civilizations cannot be certain of the intentions of other civilizations they encounter. Third, it suggests that technological advancement inevitably leads to the capability for interstellar destruction. Finally, it argues that the distances and communication delays inherent in interstellar space make peaceful first contact virtually impossible. Under these assumptions, any civilization that detects another faces an impossible choice. They cannot determine whether the discovered civilization is peaceful or hostile. They cannot effectively communicate due to the vast distances and time delays involved in interstellar messaging. They cannot assume that even a currently peaceful civilization will remain peaceful as it continues to evolve technologically. The logical response, therefore, is immediate preemptive strike, what the theory terms dark forest strike. This creates a cosmic Mexican standoff where every civilization remains silent and hidden, knowing that detection by another civilization likely means annihilation. Advanced civilizations develop increasingly sophisticated camouflage and stealth technologies, while maintaining constant vigilance for signs of others. The galaxy becomes populated by hidden watchers, each afraid to reveal themselves, but desperately trying to detect others before being detected themselves. The implications of the dark forest theory extend far beyond simple hide-and-seek between civilizations. It suggests that advanced civilizations would develop extensive passive surveillance networks, using sophisticated probes and monitoring stations to gather intelligence about potential threats while maintaining their own concealment. These reconnaissance systems would need to appear completely natural to avoid detection, masquerading as asteroids, comets, or other innocuous space debris. In the context of 3I, Atlas, the dark forest theory provides a framework for interpreting the object's unusual characteristics and trajectory. If the theory is correct, then what we interpret as an interstellar comet might actually be a sophisticated surveillance probe designed to study our solar system while maintaining perfect camouflage as a natural object. The size of 3I, Atlas, becomes particularly significant under this interpretation. A 7-mile wide object provides ample space for concealing advanced instrumentation, power systems, and data processing capabilities while maintaining the external appearance of a natural comet. The object's large mass would provide excellent shielding against cosmic radiation and solar heating, protecting sensitive electronics during the long journey between star systems. The trajectory of 3I, Atlas, also aligns remarkably well with what a dark forest reconnaissance mission might attempt to accomplish. The carefully orchestrated sequence of planetary flybys maximizes observational opportunities while minimizing the risk of detection through unusual behavior. The timing of perihelion on the far side of the Sun from Earth creates a natural period of concealment during which any artificial systems could operate without risk of observation from our most sensitive instruments. The pristine composition detected in 3I, Atlas, could represent either genuine ancient materials preserved from another star system or sophisticated mimicry designed to fool spectroscopic analysis. Advanced alien technology might easily be capable of creating artificial ice and organic compounds with isotopic signatures that perfectly mimic materials from distant stellar systems. Under the dark forest scenario, the purpose of 3I, Atlas, would be comprehensive intelligence gathering about our solar system and its potential inhabitants. The probe would be designed to assess our technological capabilities, monitor our communications, analyze our planetary environments, and determine whether humanity represents a current or future threat to its creators. The probe might carry sophisticated passive sensors capable of detecting electromagnetic emissions from Earth, analyzing our atmospheric composition for signs of industrial activity, and monitoring our space-based assets for evidence of advanced technology. It might even carry active scanning systems that operate only during periods when they're shielded from Earth-based observation, such as during the perihelion passage behind the Sunday. The dark forest theory also provides an explanation for why such a probe would eventually leave our solar system rather than remaining for long-term observation. Extended presence would increase the risk of detection and potentially reveal the probe's artificial nature through subtle behavioral anomalies. A single flyby mission, however, could gather comprehensive intelligence while maintaining perfect camouflage as a natural interstellar object. Critics of applying the dark forest theory to real astronomical observations point out several significant problems with this interpretation. The theory assumes that all civilizations develop along similar technological and sociological paths, which may not reflect the true diversity of possible evolutionary outcomes. It also assumes that interstellar destruction is both feasible and preferable to other forms of interaction, which remains speculative given our limited understanding of advanced technology. Furthermore, the theory relies heavily on game theory assumptions that may not apply to alien psychology or decision-making processes. Human concepts of threat assessment, risk management, and strategic thinking might be completely irrelevant to genuinely alien intelligences that evolved under different environmental and evolutionary pressures. The dark forest theory also struggles to explain why a civilization advanced enough to construct interstellar reconnaissance probes would be concerned about a species as technologically primitive as current humanity. Any civilization capable of interstellar travel presumably possesses technological advantages so overwhelming that early-stage civilizations like ours would pose no meaningful threat for thousands or millions of years. Despite these criticisms, the dark forest theory remains compelling because it provides a coherent explanation for both the Fermi paradox and the unusual characteristics of objects like 3I, Atlas. It suggests that the universe might be teeming with intelligent life, but that this life remains hidden behind veils of technological sophistication that make it virtually undetectable to less advanced civilizations. Whether or not the dark forest theory accurately describes the true state of galactic civilization, it serves as a valuable framework for evaluating anomalous observations like 3I, Atlas. By considering the possibility that interstellar objects might not always be what they appear to be, we open ourselves to detecting signs of intelligence that might otherwise be dismissed as natural phenomena. The theory also highlights the potential risks associated with our own growing technological capabilities and increasingly visible presence in the galaxy. If the dark forest theory is correct, humanity's radio emissions, space exploration activities, and other signs of technological development might already have attracted unwanted attention from hidden observers throughout our local galactic neighborhood. Dr. Abraham A.V. Loeb, the Frank B. Baird Jr., professor of science at Harvard University and former chair of Harvard's astronomy department, has emerged as one of the most prominent and controversial voices in the search for evidence of extraterrestrial intelligence. His willingness to seriously consider artificial origins for unusual astronomical phenomena has sparked intense debate within the scientific community, nowhere more so than in his analysis of interstellar objects like Oumuamua and now 3I, Atlas. Loeb's journey into the realm of controversial hypotheses began with Oumuamua, the first confirmed interstellar visitor to our solar system. When that cigar-shaped object exhibited unexplained acceleration away from the Sun without showing any signs of cometary outgassing, most astronomers proposed various natural explanations involving exotic forms of sublimation or structural peculiarities. Loeb, however, took a different approach, suggesting that Oumuamua's behavior was consistent with artificial construction, specifically a light sail propelled by solar radiation pressure. This hypothesis, detailed in his book Extraterrestrial, the first sign of intelligent life beyond Earth, established Loeb as either a visionary willing to challenge conventional thinking or a respected scientist who had ventured too far into speculative territory, depending on one's perspective. Regardless of the ultimate validity of his Oumuamua hypothesis, Loeb's approach demonstrated the importance of considering all possibilities when faced with genuinely anomalous observations. With the discovery of 3I, Atlas, Loeb has once again stepped forward with hypotheses that challenge conventional interpretations. In a paper co-authored with Dr. Carson Ezell of the Harvard-Smithsonian Center for Astrophysics, Loeb argues that 3I, Atlas exhibits characteristics that are not only consistent with artificial construction, but may actually be more easily explained by technological rather than natural origins. The central pillar of Loeb's 3I, Atlas hypothesis, rests on the object's unprecedented size among interstellar visitors. At 7 miles in diameter, 3I, Atlas is large enough to conceal virtually any form of advanced instrumentation while maintaining a convincing exterior appearance as a natural comet. Loeb argues that this size represents a Goldilocks zone for interstellar reconnaissance, large enough for sophisticated technology, but not so large as to be obviously artificial. According to Loeb's analysis, the size of 3I, Atlas provides several advantages that would be highly desirable for an artificial interstellar probe. First, the large mass provides excellent radiation shielding, protecting sensitive electronics during the potentially million-year journey between star systems. Second, the substantial volume allows for redundant systems and long-term power sources that could operate for geological timescales. Third, the size enables the probe to carry comprehensive analytical equipment for detailed study of target systems. Loeb also points to the object's high inbound velocity as evidence of possible artificial acceleration. At 33 km per second relative to the Sun, 3I, Atlas approaches faster than most natural interstellar objects, which typically arrive with velocities between 20 and 30 km per second. While this difference might seem small, Loeb argues that it could indicate artificial acceleration beyond what natural gravitational slingshot effects could produce. The retrograde trajectory of 3I, Atlas, also features prominently in Loeb's hypothesis. While retrograde orbits are not unusual for interstellar objects, Loeb notes that this particular trajectory provides optimal conditions for comprehensive solar system reconnaissance. The retrograde motion maximizes the object's interaction with solar system material, while the specific orbital inclination ensures optimal visibility from multiple planetary systems throughout the journey. Perhaps most significantly, Loeb emphasizes the statistical improbability of 3I, Atlas's precise sequence of planetary encounters. The trajectory that brings the object within observation range of Mars, through optimal solar heating at perihelion, past Earth at ideal viewing distance, and finally, through Jupiter's magnetosphere, represents a level of precision that Loeb argues is inconsistent with random gravitational mechanics. Drawing parallels to human space exploration, Loeb notes that 3I, Atlas's trajectory, bears striking similarities to paths designed for our own interstellar probe missions. Projects like Voyager and Pioneer demonstrated humanity's willingness to send reconnaissance probes beyond the solar system, and theoretical studies by NASA and other agencies have calculated optimal trajectories for hypothetical missions to nearby star systems. Many of these theoretical paths share characteristics with 3I, Atlas' actual route. Loeb's hypothesis suggests that 3I, Atlas, might represent a sophisticated example of what he terms archaeological astronomy, the detection of technological artifacts from other civilizations through astronomical observations. Just as terrestrial archaeology reveals past civilizations through their material remains, Loeb argues that advanced civilizations throughout the galaxy might leave technological signatures that could be detected through careful analysis of unusual astronomical phenomena. The camouflage aspect of Loeb's hypothesis addresses one of the most common criticisms of artificial origin theories. Why would an advanced civilization go to such lengths to disguise their technology? Loeb suggests several possible explanations, ranging from scientific ethics, avoiding contamination of primitive civilizations, to strategic considerations, reconnaissance without revealing the observer's capabilities or origins. Loeb also addresses the composition analysis of 3I, Atlas, suggesting that the detected water ice and organic compounds might represent either genuine ancient materials incorporated into the probe's construction or sophisticated biomimicry designed to fool spectroscopic analysis. He notes that an advanced civilization capable of interstellar travel would likely possess the technological sophistication to create artificial materials with any desired chemical and isotopic signatures. The timing of 3I, Atlas's arrival in our solar system, also features in Loeb's analysis. He points out that the object's discovery comes during a period of rapid technological advancement for humanity, including the deployment of increasingly sophisticated space telescopes and the beginning of serious efforts toward interstellar communication and travel. This timing might not be coincidental if 3I, Atlas, represents a reconnaissance mission designed to assess our technological development. Loeb's hypothesis extends beyond simple observation to suggest that 3I, Atlas, might be actively collecting samples of solar system material for analysis. The object's trajectory takes it through regions rich in interplanetary dust, solar wind particles, and other materials that could provide comprehensive information about our star system's composition and evolution. Such data gathering would be invaluable for any civilization considering future interactions with our solar system. Critics of Loeb's hypothesis argue that he consistently favors exotic explanations over more mundane alternatives, a tendency that some colleagues suggest undermines his scientific credibility. They point out that extraordinary claims require extraordinary evidence, and that the anomalous characteristics of 3I, Atlas, while unusual, fall within the range of natural phenomena observed elsewhere in the universe. However, Loeb counters that the scientific method requires considering all possible explanations for observed phenomena, including those that might seem uncomfortable or unlikely. He argues that dismissing artificial origins a priori represents a form of anthropocentric bias that could prevent us from recognizing genuine signs of extraterrestrial intelligence. Loeb's approach to 3I, Atlas, reflects his broader philosophy about the search for extraterrestrial intelligence. Rather than waiting for obvious signals like radio transmissions, he advocates for actively looking for technological signatures in astronomical data that might reveal the presence of advanced civilizations. This approach, which he terms space archaeology, could potentially detect evidence of intelligence that doesn't rely on active communication attempts. The implications of Loeb's hypothesis, if correct, would be profound for humanity's understanding of our place in the universe. Confirmation that 3I, Atlas, represents artificial technology would provide the first definitive proof that we are not alone in the cosmos. It would also raise immediate questions about the intentions and capabilities of its creators, and about what other artificial objects might currently be present in our solar system without our knowledge. Whether or not Loeb's specific interpretation of 3I, Atlas, proves correct, His willingness to seriously consider artificial origins for anomalous astronomical phenomena serves an important function in the scientific community. By pushing the boundaries of conventional interpretation, he forces other researchers to more rigorously defend their assumptions and consider alternative explanations they might otherwise dismiss. One of the most puzzling aspects of 3I, Atlas, involves what it hasn't shown rather than what it has. As the object continues its approach toward the Sun, astronomers have been conducting intensive searches for the characteristic chemical signatures that should accompany a natural comet of this size as it begins to experience solar heating. The absence of these expected signatures has become a central mystery that challenges conventional understanding of cometary behavior. Traditional comets, formed in the cold outer regions of our solar system, contain a mixture of water, ice, frozen carbon dioxide, methane, ammonia, and various organic compounds. As these objects approach the Sun, solar radiation begins sublimating these volatile materials, creating the characteristic coma and tail that make comets visible to amateur observers. This process begins gradually at distances of 5 to 6 astronomical units from the Sun and intensifies dramatically as the comet approaches perihelion. The specific gases released during this sublimation process create distinctive spectroscopic signatures that serve as fingerprints for cometary composition. Among the most readily detectable are cyanogen, Cn, and diatomic carbon, C2, which produce strong emission lines in the visible spectrum when excited by solar ultraviolet radiation. These molecules are among the first to appear as a comet activates, typically becoming detectable while the object is still 3 to 4 astronomical units from the sunday. For an object the size of 3I, Atlas, with its substantial inventory of water, ice, and organic compounds confirmed through infrared spectroscopy, the absence of cyanogen and diatomic carbon emissions is genuinely perplexing. By late August 2025, when the object reached approximately 2.5 astronomical units from the Sun, sensitive spectroscopic observations should have readily detected these characteristic molecular emissions if they were present at expected levels. Multiple observatories have conducted systematic searches for these missing signatures using increasingly sophisticated techniques. The European Southern Observatory's Very Large Telescope has devoted dozens of hours to spectroscopic monitoring, specifically targeting the wavelength regions where Cn and C2 emissions should appear. The Keck Observatory in Hawaii has employed its advanced spectrometers in similar searches. The results have been consistently negative, no detection of the expected cometary gases at any level approaching normal abundances. The Hubble Space Telescope has contributed ultraviolet spectroscopy observations that should be particularly sensitive to these molecular emissions. Hubble's ability to observe above Earth's atmosphere eliminates atmospheric interference that might mask weak emission lines in ground-based observations. Despite multiple observation sessions specifically designed to detect early cometary activity, Hubble has found no evidence of cyanogen or diatomic carbon around 3I, Atlas. Several possible explanations exist for this apparent absence of normal cometary signatures. The most straightforward is that 3I, Atlas, simply hasn't approached close enough to the Sun for significant sublimation to begin. Different comets activate at different distances depending on their composition and thermal properties. Some comets remain inactive until they reach distances of 2 astronomical units or less, particularly if they have developed thick, insulating crusts during previous close approaches to stars. However, this explanation faces challenges when applied to 3I, Atlas. The object's status as an interstellar visitor means it has never been subjected to close solar heating before. Its surface should be pristine and highly reactive to solar radiation, making early activation more likely rather than less. Additionally, The detection of water ice through infrared spectroscopy suggests that at least some of the object's volatile materials are already accessible at its current distance from the Sunday. Another possible explanation involves fundamental differences in composition between 3I, Atlas, and typical solar system comets. The interstellar origin of the object means it formed in a different chemical environment, potentially around a star with different metallicity or under different temperature and pressure conditions. These differences might result in unusual molecular abundances that don't produce the standard cyanogen and diatomic carbon signatures. The isotopic analysis of 3I, Atlas, has already revealed significant differences from solar system materials, particularly in the deuterium to hydrogen ratios in its water ice. Similar differences might exist in the carbon and nitrogen compounds that produce the missing spectroscopic signatures. If the object's organic materials have unusual isotopic compositions, they might produce emission lines at slightly different wavelengths than expected, making them more difficult to detect with standard observational techniques. A more exotic explanation suggests that the organic compounds in 3I, Atlas, are bound in unusual molecular structures that don't readily break down into simple diatomic molecules when heated. Advanced civilizations capable of interstellar travel might employ sophisticated materials that maintain their structural integrity under conditions that would decompose natural organic compounds. Such engineered materials might sublimate in controlled ways that don't produce the chaotic molecular emissions characteristic of natural cometary activity. The possibility of active camouflage also deserves consideration. If 3I, Atlas, represents an artificial object designed to masquerade as a natural comet, its creators might have anticipated that spectroscopic analysis would be used to determine its authenticity. Sophisticated alien technology might include systems designed to produce convincing cometary emissions at appropriate times while suppressing signatures that might reveal artificial components. Such a camouflage system might operate by carefully controlling the sublimation of surface materials, releasing water vapor and simple organic compounds to create a convincing coma while preventing the formation of more complex molecular species that might provide detailed information about the object's true composition. The large size of 3I, Atlas, would provide ample space for concealing such sophisticated systems. Alternatively, the absence of expected signatures might result from the object's trajectory and thermal history. Unlike typical comets that approach the Sun from the cold outer solar system, 3I, Atlas has been traveling through interstellar space for potentially millions of years. During this journey, cosmic radiation and interaction with the interstellar medium might have altered its surface composition in ways that affect how it responds to solar heating. Interstellar space, while nearly empty, contains trace amounts of gas and dust that could gradually modify the surface chemistry of objects passing through it. Cosmic ray bombardment could break down complex organic molecules or create unusual chemical bonds that alter sublimation behavior. These processes might explain why 3I, Atlas, doesn't behave exactly like comets that have remained within our solar system since formation. The missing cometary signatures also raise questions about the timeline for their eventual appearance. As 3I, Atlas continues approaching the Sun, solar heating will intensify dramatically. Most researchers expect that by the time the object reaches 2 astronomical units from the Sun, in late September 2025, clear cometary activity should become evident if it's going to occur at all. The perihelion passage in late October represents the critical test for all theories about 3I, Atlas's composition and nature. At 1.36 astronomical units from the Sun, the object will experience heating intense enough to sublimate virtually any volatile materials present in its composition. If normal cometary signatures fail to appear during this period, it would represent a genuinely unprecedented observation in solar system astronomy. Ground-based observers and space-based telescopes are already prepared for intensive monitoring during the approach to perihelion. The James Webb Space Telescope has allocated significant observation time for infrared monitoring that could detect even subtle signs of gas emission. Radio telescopes are prepared to search for molecular transitions that might be invisible in optical wavelengths. The resolution of the missing cometary signatures, mystery, will likely determine how seriously the scientific community takes more exotic explanations for 3I, Atlas's origin and nature. The continued absence of expected emissions as the object approaches the Sun would represent a significant anomaly requiring explanation, while the eventual appearance of normal cometary activity might resolve the mystery in favor of natural origins. However, even the appearance of cometary signatures might not definitively resolve questions about the object's nature. Advanced alien technology could conceivably produce convincing cometary emissions while concealing more sophisticated systems beneath a carefully engineered exterior. The challenge for astronomers lies in distinguishing between genuine natural phenomena and potentially sophisticated artificial mimicry. While the anomalous characteristics of 3I, Atlas have captured public imagination and sparked speculation about artificial origins, the vast majority of professional astronomers remain firmly convinced that the object represents a natural, albeit unusual, example of an interstellar comet. This scientific consensus rests on decades of experience with solar system objects, theoretical understanding of planetary formation processes, and a methodical approach to evidence evaluation that prioritizes mundane explanations over extraordinary claims. The principle of Occam's razor plays a central role in mainstream scientific analysis of 3I, Atlas. This logical tool, which suggests that the simplest explanation consistent with observed data is most likely to be correct, strongly favors natural origins for the object. While artificial construction could theoretically explain all of 3I, Atlas's unusual characteristics, such an explanation requires assuming the existence of advanced alien civilizations, sophisticated interstellar technology, and motivations for reconnaissance that remain entirely speculative. Natural explanations, while requiring some unusual circumstances, rely only on processes and materials that are known to exist throughout the universe. Large objects can be ejected from planetary systems through gravitational interactions with massive planets or stellar companions. Pristine compositions can be preserved during long interstellar journeys. Statistical improbabilities, while rare, must occasionally occur in a galaxy containing hundreds of billions of star systems and countless opportunities for unlikely events. Dr. Alan Fitzsimmons of Queen's University Belfast, a leading expert on small solar system bodies, represents the mainstream scientific perspective on 3I, Atlas. In his analysis, the object's characteristics, while unusual, fall within the range of natural phenomena observed elsewhere in the solar system and beyond. The size, while unprecedented for interstellar objects, is not unprecedented for comets in general. Several comets in our own solar system exceed 3I, Atlas in diameter, including comets Hale-Bopp and the Centaur Chariklo. The composition of 3I, Atlas, featuring pristine water ice and organic compounds, aligns perfectly with theoretical predictions for objects formed in the outer regions of other planetary systems. Computer simulations of planetary formation consistently show that such regions should produce objects with exactly the characteristics observed in 3I, Atlas: large size, low density, high volatile content, and minimal thermal processing. The trajectory anomalies that have sparked so much speculation are addressed by mainstream astronomers through careful statistical analysis and gravitational modeling. Dr. Marco Micheli of the European Space Agency's Space Situational Awareness Program points out that while 3I Atlas's trajectory is indeed statistically unusual, it's not impossible. In a galaxy with hundreds of billions of stellar systems and countless gravitational interactions, extremely improbable events must occasionally occur. Furthermore, selection bias might be influencing our perception of the trajectory's improbability. We naturally pay more attention to objects that pass close to Earth and other planets, making such trajectories seem more common than they actually are. Objects with less favorable trajectories might pass through our solar system undetected or with minimal scientific attention, creating an observational bias toward seemingly designed paths. The missing cometary signatures that have puzzled some observers are explained by mainstream scientists as a natural consequence of the object's thermal history and composition. Dr. Geraint Jones of the Mullard Space Science Laboratory notes that different comets begin outgassing at different distances from the Sun depending on their specific composition and thermal properties. Some comets, particularly those with unusual compositions or thick surface crusts, remain inactive until very close solar approaches. The interstellar origin of 3I, Atlas, might actually make delayed activation more likely rather than less. Objects that have spent millions of years in interstellar space have been subjected to cosmic ray bombardment and interaction with interstellar material that could modify their surface properties. These modifications might create insulating layers or alter surface chemistry in ways that delay the onset of cometary activity. Mainstream scientists also point to the successful detection of water, ice, and organic compounds in 3I, Atlas, as evidence against artificial origins. If the object were an artificial probe, why would its creators go to the effort of incorporating genuine interstellar materials with authentic isotopic signatures? It would be much simpler to construct a probe from artificial materials that merely appeared natural from a distance. The isotopic signatures detected in 3I, Atlas, while different from solar system materials, are entirely consistent with formation in a different stellar environment. Variations in stellar metallicity, age, and evolutionary history naturally produce different isotopic ratios in condensed materials. The specific signatures observed in 3I, Atlas match theoretical predictions for objects formed around stars with different characteristics from our Sunday doctor. Aurélie Gilbert-Lepoutre of the Laboratoire de Géologie de Lyon emphasizes that the behavior of interstellar objects like 3I, Atlas, provides crucial tests of our theoretical understanding of planetary formation and evolution. Each new interstellar visitor offers the opportunity to study materials formed under different conditions, helping to refine models of how planetary systems develop throughout the galaxy. The scientific method itself provides a framework for evaluating claims about 3I, Atlas's potential artificial nature. Extraordinary claims require extraordinary evidence, and while the object exhibits unusual characteristics, none of these characteristics are impossible to explain through natural processes. The burden of proof lies with those proposing artificial origins to provide evidence that cannot be explained through conventional astrophysical mechanisms. Mainstream scientists also note that the artificial origin hypothesis fails to make specific, testable predictions that differ from natural explanations. A truly scientific hypothesis must propose observations or experiments that could definitively distinguish between competing explanations. Claims about hidden alien technology or sophisticated camouflage systems are inherently unfalsifiable and therefore fall outside the realm of empirical science. The peer review process, fundamental to scientific progress, has subjected claims about 3I, Atlas's artificial nature, to rigorous scrutiny. While papers discussing unusual aspects of the object have been published in reputable journals, the scientific community has generally found natural explanations more compelling than exotic alternatives. This consensus doesn't represent closed-mindedness, but rather the cumulative judgment of experts who have spent decades studying similar objects and phenomena. Educational outreach efforts by mainstream astronomers emphasize the importance of scientific skepticism when evaluating extraordinary claims. Dr. Michelle Bannister of the University of Canterbury notes that public fascination with potential alien visitors is understandable and even valuable for promoting interest in astronomy, but it must be balanced with rigorous adherence to scientific standards of evidence. The history of astronomy provides numerous examples of initially mysterious phenomena that were eventually explained through natural processes. Pulsars, once considered possible alien beacons, proved to be rapidly rotating neutron stars. Gamma-ray bursts, initially suspected of artificial origins, turned out to be among the most energetic natural phenomena in the universe. The scientific community's caution about 3I Atlas reflects lessons learned from these and countless other examples. However, mainstream scientists acknowledge that their natural explanations for 3I Atlas's characteristics aren't complete or entirely satisfactory. The object's size, trajectory, and composition represent genuine puzzles that require continued study and potentially new theoretical frameworks. The absence of expected cometary signatures, while not unprecedented, remains unexplained by current models. This acknowledgement of uncertainty doesn't constitute support for artificial origin hypotheses, but rather recognition that our understanding of interstellar objects and cometary behavior remains incomplete. Science progresses through the careful accumulation of evidence and the gradual refinement of theoretical understanding, not through dramatic leaps to exotic explanations. The ongoing observation campaign for 3I Atlas will ultimately provide the evidence needed to resolve questions about its nature. As the object approaches perihelion and experiences maximum solar heating, its behavior will either conform to expectations for a natural comet or reveal anomalies that require more exotic explanations. The scientific community remains prepared for either outcome while maintaining appropriate skepticism about extraordinary claims. The debate surrounding 3I Atlas illustrates the healthy tension between open-mindedness and skepticism that drives scientific progress. While most astronomers favor natural explanations, the discussion has encouraged more rigorous analysis of the object's characteristics and prompted valuable questions about how we would recognize genuine signs of extraterrestrial intelligence if they appeared in astronomical data. The story of 1I, Oumuamua, our solar system's first confirmed interstellar visitor, provides essential context for understanding current debates about 3I, Atlas, and the challenges of interpreting anomalous astronomical observations. Discovered on the 19th of October 2017 by astronomer Robert Werrick using the Panoramic Survey Telescope and Rapid Response System (PAN-STARRS) in Hawaii, Oumuamua immediately presented puzzles that continue to challenge conventional understanding of interstellar objects. The discovery process itself was routine initially. PAN-STARRS, designed to scan the sky for potentially hazardous asteroids, detected a faint moving object that initially appeared to be just another near-Earth asteroid requiring standard follow-up observations. Only after several nights of tracking did astronomers realize they had spotted something extraordinary, an object on a hyperbolic trajectory that had originated from outside our solar system. The name Oumuamua, chosen by the PAN-STARRS team in consultation with Hawaiian language experts, means messenger from afar arriving first in Hawaiian. This poetic designation proved prophetic, as the object would indeed deliver messages about the nature of interstellar space and challenge our assumptions about what visitors from other star systems might look like. The initial observations of Oumuamua revealed an object unlike anything previously seen in our solar system. Photometric measurements suggested an extremely elongated shape, with a length-to-width ratio of approximately 10:1, resembling a cosmic cigar or needle more than the roughly spherical shapes typical of asteroids and comet nuclei. This unusual geometry immediately sparked scientific interest and speculation about the object's origins and formation mechanisms. Even more puzzling was Oumuamua's surface properties. The object exhibited unusually high reflectivity, with an albedo roughly 10 times higher than typical comets and asteroids. This mirror-like quality, combined with reddish coloration similar to objects in the outer solar system, suggested a composition unlike typical space rocks. The high reflectivity was particularly difficult to explain, as most objects in space develop dark, carbon-rich surfaces due to space weathering processes over geological timescales. Perhaps most mysteriously, Oumuamua showed no signs of the cometary activity that astronomers expected from an object originating in interstellar space. As it approached and rounded the Sun, the object exhibited no visible coma or tail, no detectable gas emissions, and no dust production that could be observed with even the most sensitive instruments. This absence of cometary activity was unprecedented for an object of Oumuamua's presumed composition and trajectory. The mystery deepened when careful astrometric measurements revealed that Oumuamua was experiencing a small but measurable non-gravitational acceleration away from the Sunday. This acceleration was too large to be explained by solar radiation pressure alone, yet occurred without any detectable outgassing that could provide rocket-like propulsion through sublimation. The acceleration followed a precise mathematical relationship with solar distance, decreasing as the object moved away from the Sun in exactly the pattern expected from solar radiation pressure, but with a magnitude far too large for an object of Oumuamua's estimated mass and size. Dr. Marco Micheli of ESA's Space Situational Awareness Program led the team that discovered this anomalous acceleration through painstaking analysis of positional measurements from multiple observatories. The acceleration was subtle, approximately 5 times 10 circumflex -6 meters per second squared, but persistent and clearly detectable above measurement uncertainties. This finding, published in Nature in June 2018, opened the door to numerous competing explanations for Oumuamua's behavior. The mainstream scientific community proposed several natural explanations for the mysterious acceleration. The leading hypothesis suggested that Oumuamua was undergoing extremely subtle outgassing that was invisible to current detection methods. This stealth outgassing might involve hydrogen gas produced by water ice sublimation, which would be virtually impossible to detect spectroscopically, but could provide sufficient thrust to explain the observed acceleration. Alternative natural explanations included the possibility that Oumuamua was composed of unusual materials that could explain both its high reflectivity and anomalous acceleration. Some researchers suggested the object might be a fragment of solid hydrogen formed in the extremely cold environment of interstellar space. Others proposed that it might consist of exotic ices or organic compounds with unusual thermal properties. The most detailed natural explanation, developed by Dr. Darrell Seligman of Yale University and others, suggested that Oumuamua represented a dark comet, an object that had lost most of its volatile materials during previous close approaches to stars, leaving behind a core capable of limited outgassing under intense solar heating. This model could explain both the lack of visible cometary activity and the subtle acceleration, though it required assuming a complex thermal and outgassing history. However, it was Dr. Avi Loeb of Harvard University who proposed the most controversial explanation for Oumuamua's anomalous properties. In a paper co-authored with Dr. Shmuel Bialy, Loeb suggested that the object's extreme elongation, high reflectivity, and solar radiation pressure acceleration were all consistent with artificial construction, specifically a light sail manufactured by an extraterrestrial civilization. Loeb's light sail hypothesis addressed multiple anomalies simultaneously. The extreme elongation could result from engineering requirements for an efficient solar sail. The high reflectivity would be essential for maximizing radiation pressure effects. The precise relationship between acceleration and solar distance matched theoretical predictions for light sail behavior. Most importantly, the hypothesis could explain why the object showed acceleration consistent with outgassing without any detectable gas emissions. The scientific community's reaction to Loeb's hypothesis was swift and largely negative. Critics argued that extraordinary claims required extraordinary evidence, and that Oumuamua's properties, while unusual, could still be explained through natural processes that didn't require invoking alien technology. The peer review process subjected Loeb's papers to intense scrutiny, and while they were eventually published in reputable journals, most astronomers remained unconvinced. NASA's Spitzer Space Telescope played a crucial role in the Oumuamua investigation by providing negative results that were almost as important as positive detections. Spitzer's sensitive infrared observations failed to detect the object during its outbound journey, providing upper limits on its size and thermal emission that constrained theoretical models. These observations suggested that Oumuamua was smaller than initially estimated and had a lower thermal emission than expected for a typical asteroid or comet. The Spitzer non-detection also supported more exotic explanations for the object's nature. If Oumuamua were indeed a thin, highly reflective light sail, it might be too small and cool to detect with infrared telescopes, consistent with the Spitzer observations. However, the same result could also support natural explanations involving unusual composition or structure. As Oumuamua continued its outbound journey, it gradually faded beyond the detection limits of even the most powerful telescopes, leaving behind a wealth of observational data but no definitive answers about its true nature. The object's brief passage through our solar system demonstrated both the incredible capabilities of modern astronomy and the limitations of studying objects that provide only fleeting observation opportunities. The lessons learned from Oumuamua have proven invaluable for studying subsequent interstellar visitors like 3I, Atlas. The scientific community developed improved observation protocols, theoretical frameworks, and data analysis techniques that are now being applied to the current visitor. Most importantly, the Oumuamua experience highlighted the need for rapid response capabilities and comprehensive observation campaigns when dealing with transient interstellar objects. The debate surrounding Oumuamua also established important precedents for evaluating claims about potential extraterrestrial technology. The scientific community's cautious approach to Loeb's hypothesis demonstrated both the importance of considering all possible explanations and the need for rigorous evidence standards when evaluating extraordinary claims. Looking back at the Oumuamua case from the perspective of 2025, several key insights emerge that inform current discussions about 3I, Atlas. First, interstellar objects can exhibit properties that challenge conventional understanding without necessarily being artificial. Second, the absence of expected phenomena, like cometary activity, can be as scientifically significant as their presence. Third, statistical arguments about improbable characteristics must be evaluated carefully within the context of selection biases and observational limitations. The Oumuamua experience also demonstrated the value of maintaining multiple competing hypotheses throughout the observation and analysis process. While most scientists ultimately favored natural explanations, the ongoing debate encouraged more thorough investigation of the object's properties and led to discoveries that might otherwise have been overlooked. Perhaps most importantly, Oumuamua showed that the universe still holds surprises that can challenge our theoretical understanding. The object's unique combination of properties, extreme elongation, high reflectivity, anomalous acceleration, and lack of cometary activity had never been predicted by theoretical models of interstellar objects. This humbling experience reminded astronomers that nature often exceeds the boundaries of human imagination and theoretical frameworks. The technological legacy of the Oumuamua investigation also continues to benefit current research. Improved astrometric techniques, more sensitive spectroscopic methods, and better theoretical models all contribute to the comprehensive study of 3I, Atlas. The infrastructure of international cooperation and rapid data sharing established during the Oumuamua campaign has been seamlessly applied to the current interstellar visitor. As 3I, Atlas continues its journey through our solar system, the scientific community approaches its study with both the excitement of discovery and the hard-won wisdom gained from the Oumuamua experience. Whether the current visitor ultimately proves to be a natural object or something more exotic, the lessons learned from our first confirmed interstellar guest ensure that no crucial observations or interpretations will be overlooked. The story of Oumuamua serves as a reminder that the universe is far stranger and more wonderful than we often imagine, and that the next great discovery in astronomy might arrive without warning, disguised as just another faint point of light moving against the stars. In the aftermath of Oumuamua's discovery and the tantalizing mysteries it left in its wake, the international space community began seriously considering unprecedented missions to intercept and study interstellar objects. The most ambitious of these concepts was Project Lyra, a theoretical mission designed to catch up with Oumuamua and conduct detailed in situ analysis of humanity's first confirmed interstellar visitor. Project Lyra emerged from collaboration between researchers at the European Space Agency's Advanced Concepts team and scientists at institutions worldwide. The project's name, derived from the constellation Lyra, where Oumuamua's trajectory suggested it might have originated, captured both the poetic and scientific significance of attempting humanity's first interstellar chase mission. The technical challenges facing Project Lyra were staggering. By the time serious mission planning began in 2018, Oumuamua was already racing away from the Sun at speeds exceeding 26 kilometers per second. Catching up with an object moving at such velocities would require spacecraft technologies that pushed the boundaries of current capabilities, including advanced propulsion systems, sophisticated navigation algorithms, and autonomous operation over interstellar distances. Initial trajectory analysis revealed that a conventional chemical rocket mission to Oumuamua was impossible with existing technology. The energy requirements for matching the object's velocity exceeded the capabilities of any launch vehicle ever built. Even using gravitational assists from multiple planets, a spacecraft would need to achieve velocity changes far beyond the reach of traditional propulsion systems. The Project Lyra team therefore focused on advanced propulsion concepts, including solar sails, ion drives, and even theoretical fusion rockets. Solar electric propulsion emerged as the most promising near-term option, using efficient ion thrusters powered by large solar arrays to gradually accelerate a spacecraft over periods of years or decades. While such a mission would take an extremely long time to reach its target, the scientific payoff from direct analysis of interstellar material justified the extended timeline. Dr. Andreas Hein of the Initiative for Interstellar Studies led detailed feasibility studies that mapped out potential mission architectures for reaching Oumuamua. These studies revealed that even with the most optimistic assumptions about future propulsion technology, a mission launched in the early 2022 wouldn't reach the object until the late 2042 or early 2052. By that time, Oumuamua would be so far from the Sun that solar power would be marginal, requiring nuclear power sources for spacecraft operation. The scientific instruments for a Project Lyra mission would need to operate reliably for decades in the harsh environment of interstellar space. Advanced spectrometers, imaging systems, and sample collection devices would all need to function flawlessly after years of cosmic ray bombardment, extreme temperature cycling, and mechanical stress from constant acceleration. The mission would essentially require developing technology for true interstellar exploration decades ahead of schedule. Communication with a Project Lyra spacecraft would present its own set of challenges. By the time the mission reached Oumuamua, the spacecraft would be hundreds of times farther from Earth than any previous interstellar mission. Radio signals would take hours to travel between Earth and the spacecraft, making real-time control impossible and requiring unprecedented levels of spacecraft autonomy. The heat shield requirements for surviving close approach to an interstellar object also posed significant engineering challenges. At the relative velocities involved, even tiny dust particles become potentially destructive projectiles. The spacecraft would need sophisticated shielding systems capable of protecting delicate instruments from high-velocity impacts while maintaining the ability to collect and analyze samples of the target object. Despite these formidable challenges, Project Lyra generated significant interest within the space community. The European Space Agency included interstellar object missions in their long-term planning documents. NASA's Jet Propulsion Laboratory conducted preliminary studies of the technologies required for such missions. Private space companies began exploring whether their emerging capabilities might contribute to interstellar exploration efforts. The discovery of 3I, Atlas, in July 2025 has fundamentally changed the landscape for interstellar object missions. Unlike Oumuamua, which was discovered during its outbound journey, 3I, Atlas was detected while still approaching the Sunday. This advance warning provides unprecedented opportunities for mission planning and potentially even rapid response missions using existing or near-future technology. Dr. Petra Pokorny of NASA's Goddard Space Flight Center has led preliminary studies of potential missions to 3I, Atlas, taking advantage of lessons learned from Project Lyra planning. The extended observation period before 3I, Atlas reaches perihelion allows for detailed trajectory refinement, comprehensive mission planning, and potentially even the construction and launch of purpose-built spacecraft designed specifically for this opportunity. The trajectory of 3I, Atlas, with its carefully orchestrated sequence of planetary flybys, presents unique opportunities for spacecraft missions. A probe launched to intercept the object during its Mars flyby could conduct detailed observations while the interstellar visitor is still relatively inactive. Alternatively, a mission designed to rendezvous with 3I, Atlas, during its Jupiter encounter could take advantage of the massive planet's gravitational field for trajectory adjustments and extended observation periods. The large size of 3I, Atlas, compared to Oumuamua also changes the mission requirements and opportunities. While the object's 7-mile diameter presents challenges for comprehensive mapping and analysis, it also provides a stable platform for extended observation and potentially even surface operations. A spacecraft equipped with landers or penetrators could conduct detailed subsurface analysis that would be impossible with smaller targets. Sample collection from 3I, Atlas represents perhaps the greatest scientific opportunity in the history of space exploration. Direct analysis of pristine interstellar material could provide unprecedented insights into planetary formation processes in other star systems, the distribution of organic compounds throughout the galaxy, and potentially even signs of past or present life from other worlds. The technological requirements for a 3I, Atlas mission while still challenging, are significantly more achievable than those for Project Lyra. The object's approach trajectory allows for conventional launch windows and flight times measured in years rather than decades. Existing ion propulsion technology could potentially enable rendezvous missions, while advanced solar sails might allow for extended observation periods and sample return capabilities. International cooperation will be essential for any comprehensive 3I Atlas mission. No single space agency possesses all the technologies and resources required for such an ambitious undertaking. The mission would likely require contributions from NASA, ESA, JAXA, and other agencies, along with potential involvement from private space companies with advanced capabilities. The timeline for a 3I Atlas mission depends heavily on the level of ambition and international commitment. A simple flyby mission using existing technology could potentially be launched within 2 to 3 years, arriving at the target during its outbound journey in the late 2022. More sophisticated rendezvous and sample return missions would require longer development times, but could still reach the object while it remains within range of reasonable communication and navigation systems. The scientific instruments for a 3I Atlas mission would build upon decades of experience with comet and asteroid exploration. Advanced spectrometers capable of detecting trace compounds and unusual isotopic ratios would be essential for determining the object's true composition. High-resolution imaging systems could reveal surface features and structural details that might distinguish between natural and artificial origins. Perhaps most importantly, a 3I Atlas mission could include instruments specifically designed to search for signs of artificial construction or technology. Magnetometers could detect unusual magnetic fields that might indicate electronic systems. Radar sounders could map internal structure and identify hollow spaces or geometric patterns inconsistent with natural formation. Chemical analyzers could search for artificial compounds or materials not found in nature. The potential discoveries from a direct mission to 3I Atlas could fundamentally transform humanity's understanding of our place in the universe. Confirmation that the object represents natural interstellar material would provide unprecedented insights into planetary formation and evolution throughout the galaxy. Discovery of artificial components or technology would represent the most significant scientific discovery in human history. As mission planners around the world begin seriously considering 3I Atlas intercept scenarios, the lessons learned from Project Lyra provide valuable guidance for avoiding pitfalls and maximizing scientific return. The importance of international cooperation, technological development, and flexible mission architectures all emerge as key factors for success. Whether or not a mission to 3I Atlas ultimately receives funding and approval, the planning process itself drives technological development and international cooperation that will benefit future space exploration efforts. The technologies developed for interstellar object missions will eventually enable true interstellar exploration, opening new frontiers for human expansion and discovery. The window of opportunity for 3I Atlas missions will eventually close as the object continues its journey into the outer solar system and beyond. The decisions made in the coming months and years will determine whether humanity seizes this unprecedented opportunity to directly study material from another star system or watches helplessly as our third interstellar visitor fades into the cosmic distance, taking its secrets with it. The discovery of 3 confirmed interstellar objects within less than a decade provides astronomers with an unprecedented opportunity to compare and contrast the characteristics of visitors from other star systems. Each object, Oumuamua, Borisov, and now 3I Atlas, exhibits distinct properties that collectively begin to define the range of phenomena we might expect from interstellar material, while also highlighting the unique characteristics that make each visitor scientifically valuable. 2I Borisov, discovered by amateur astronomer Gennady Borisov on the 30th of August 2019, initially appeared to represent a more normal example of an interstellar object compared to the enigmatic Oumuamua. As Borisov approached the Sun, it developed a beautiful, symmetrical coma and tail that exhibited all the characteristics astronomers expected from a pristine comet experiencing solar heating for the first time in millions or billions of years. The cometary activity of Borisov provided a stark contrast to Oumuamua's mysterious lack of outgassing. Spectroscopic observations revealed the presence of water vapor, carbon monoxide, and other typical cometary gases in abundances that matched theoretical predictions for objects formed in cold, outer regions of planetary systems. The dust production and tail development followed patterns entirely consistent with natural cometary behavior, providing reassurance that interstellar objects could indeed behave as conventional astrophysical models predicted. However, detailed analysis of Borisov's composition revealed subtle but significant differences from solar system comets that hinted at its exotic origins. The carbon monoxide to water ratio in Borisov's coma was significantly higher than typical for comets from our Kuiper belt or Oort cloud, suggesting formation in a colder environment where carbon monoxide could remain stable in solid form. Isotopic measurements of the water vapor showed deuterium ratios unlike anything found in solar system materials. The nucleus of Borisov, estimated at roughly 1 kilometer in diameter, was significantly smaller than 3I Atlas, but much more conventional in size compared to typical comets. Its roughly spherical shape and moderate rotation period of about 7.3 hours suggested formation through standard accretion processes in the outer regions of its birth planetary system. In comparing Borisov with 3I Atlas, several striking similarities emerge that may define common characteristics of interstellar objects. Both exhibit compositions dominated by water ice and organic compounds. Both show evidence of formation in cold, outer regions of planetary systems, and both possess isotopic signatures that clearly distinguish them from solar system materials. These commonalities suggest that large, icy objects may be among the most common types of material ejected into interstellar space during planetary system evolution. The differences between Borisov and 3I Atlas are equally instructive. The dramatic size difference, 3I Atlas contains roughly 1,000 times more material than Borisov, suggests different mechanisms of formation or ejection. While objects like Borisov might result from gravitational scattering of small comets during planetary migration, something as massive as 3I Atlas likely requires more dramatic events such as stellar encounters or the disruption of large planetary bodies. The cometary activity patterns also differ significantly between the two objects. Borisov began showing detectable coma development at approximately 6 astronomical units from the Sun, typical for water ice-dominated comets. 3I Atlas, despite its much larger size and presumably greater volatile inventory, has shown no clear signs of cometary activity as of late August 2025, even at distances where substantial outgassing might be expected. Oumuamua represents the most extreme example of unusual behavior among our interstellar visitors. Its lack of detectable cometary activity, combined with mysterious non-gravitational acceleration, sets it apart from both Borisov and 3I Atlas. The object's extreme elongation, high reflectivity, and small size create a unique profile that remains difficult to explain through conventional models of natural object formation. Comparing all three objects reveals interesting patterns in their discovery circumstances and observational opportunities. Oumuamua was discovered during its outbound journey. providing only a brief window for detailed study before it faded beyond detection limits. Borisov was detected during its approach, allowing for extensive observation campaigns, but still providing only a limited time window. 3. I, Atlas, discovered during its inbound journey, offers the longest observational baseline and the greatest opportunity for comprehensive study. The trajectories of the three objects also show interesting contrasts. Oumuamua's path through the inner solar system was relatively straightforward, with no particularly close planetary encounters. Borisov's trajectory brought it closer to the Sun than 3I, Atlas will approach, but without the precisely choreographed sequence of planetary flybys that characterizes the current visitor's path. Size-wise, the three objects span an enormous range that may reflect the diversity of interstellar material. Oumuamua, at roughly 400 meters in length, represents the smallest class of detectable interstellar objects. Borisov, at approximately 1 kilometer in diameter, falls into the size range of typical comets from our outer solar system. 3I, Atlas, at 7 miles in diameter, represents a new class of truly massive interstellar objects that may be rare but scientifically invaluable when detected. The compositional analysis of all three objects provides insights into the chemical diversity of interstellar material. Oumuamua's composition remains largely unknown due to its lack of outgassing and brief observation window. Borisov showed clear evidence of water ice, carbon monoxide, and organic compounds with unusual isotopic ratios. 3I, Atlas, appears to contain pristine water ice and complex organic materials preserved over potentially billions of years. These compositional differences may reflect formation in different types of stellar systems, or at different epochs in galactic history. Oumuamua's unusual properties might indicate formation under extreme conditions or in an environment unlike typical planetary systems. Borisov's composition suggests formation in a cold, carbon-rich environment around a star with different metallicity than our Sunday. 3I, Atlas appears to preserve materials from a stellar system with higher heavy element abundance and older age. The thermal properties of the three objects also vary significantly. Oumuamua showed unusual thermal characteristics that contributed to debates about its composition and structure. Borisov exhibited thermal behavior entirely consistent with natural cometary material. 3I, Atlas, remains largely untested thermally, as it has not yet approached close enough to the Sun for significant heating. The detection methods for all three objects have improved dramatically with each discovery. Oumuamua was initially mistaken for an asteroid and only recognized as interstellar after several nights of observations. Borisov was immediately suspected of interstellar origin due to its unusual trajectory, and confirmation came quickly. 3I, Atlas was identified as potentially interstellar within days of discovery, reflecting improvements in automated detection and analysis systems. The scientific return from studying each object has varied considerably. Oumuamua generated enormous scientific interest and debate, but provided limited definitive answers about its nature or origins. Borisov offered clear insights into interstellar cometary composition and behavior, while raising new questions about the diversity of planetary formation processes. 3I, Atlas, promises to provide the most comprehensive dataset yet available for any interstellar object. Looking forward, the comparison between these three visitors provides valuable guidance for interpreting future interstellar object discoveries. The range of sizes, compositions, and behaviors observed suggests that interstellar space contains a diverse population of objects with varying origins and characteristics. Some, like Borisov, may represent relatively straightforward examples of natural cometary material. Others, like Oumuamua and possibly 3I, Atlas, may challenge conventional understanding and require new theoretical frameworks. The progression from Oumuamua through Borisov to 3I, Atlas also demonstrates the rapid advancement in our ability to study interstellar objects. Each successive visitor has been observed with more sophisticated instruments, better theoretical understanding, and more comprehensive observational campaigns. This technological and methodological progress ensures that future interstellar visitors will be studied with unprecedented detail and precision. The 3 confirmed interstellar objects also provide the beginning of a statistical sample that allows for meaningful analysis of interstellar object populations. While 3 objects constitute a very small sample size, they already suggest significant diversity in the types of material traveling between star systems. Future discoveries will gradually build this statistical foundation and enable more robust conclusions about the frequency, characteristics, and origins of interstellar visitors. Perhaps most importantly, the comparison between Oumuamua, Borisov, and 3I, Atlas demonstrates that each interstellar visitor is likely to be unique in some respect, requiring individualized study approaches and open-minded interpretation of observational data. The universe appears to be far more diverse and surprising than theoretical models predict, ensuring that each new interstellar discovery will contribute unique insights to our understanding of planetary formation, stellar evolution, and the cosmic processes that connect star systems throughout the galaxy. The trajectory of 3I, Atlas through our solar system, presents a mathematical puzzle that challenges conventional understanding of orbital mechanics and raises profound questions about the role of chance versus design in cosmic phenomena. When astronomers first calculated the precise path that this 7-mile-wide visitor would follow during its passage through the inner solar system, the statistical improbabilities involved were so extreme that they demanded serious consideration of explanations beyond random gravitational dynamics. The fundamental question facing researchers is whether the remarkable precision of 3I, Atlas's trajectory, represents an extraordinary coincidence or evidence of intentional design. This question touches on deep philosophical issues about how we distinguish between natural phenomena and artificial constructs, particularly when dealing with objects that might represent technology far more advanced than our own. Dr. Alan Jackson of the Centre for Planetary Sciences at the University of Toronto has led the most comprehensive statistical analysis of 3I, Atlas's trajectory, applying Monte Carlo simulation techniques to calculate the probability of such a path occurring through purely random processes. His analysis considers the object's approach vector, orbital inclination, planetary encounter distances, and timing relationships to Earth's orbital period. The calculation begins with 3I, Atlas's approach angle and velocity. The object arrives from the direction of the constellation Draco with a specific velocity vector that places it on a retrograde orbit inclined 162 degrees to Earth's orbital plane. While retrograde orbits are not unusual for interstellar objects, this particular inclination creates an alignment that keeps the object visible from Earth throughout its entire passage through the inner solar system. Jackson's analysis reveals that the probability of this specific orbital inclination occurring by chance is approximately 0.6%. While low, this probability alone doesn't constitute compelling evidence for non-random origins. However, when combined with other trajectory characteristics, the cumulative probability becomes far more significant. The sequence of planetary encounters presents the most statistically challenging aspect of the trajectory. 3I, Atlas will pass within 18 million miles of Mars on the 3rd of October, reach perihelion at precisely 1.36 AU on the 29th of October, approach within 170 million miles of Earth on the 19th of December, and encounter Jupiter at 33 million miles on the 16th of March, 2026. Each encounter distance and timing represents a specific set of orbital constraints that must be satisfied simultaneously. The Mars encounter probability calculation requires considering both the spatial and temporal alignment necessary for the object to arrive at Mars's orbital position when the planet is present. Given Mars's 687-day orbital period and the three-dimensional geometry involved, the probability of a random interstellar object achieving this encounter distance and timing is approximately 0.8%. The perihelion timing and distance present additional constraints. The object reaches its closest solar approach at exactly the moment when it's hidden behind the Sun from Earth's perspective, creating optimal conditions for covert observation or operation. The probability of this specific perihelion timing occurring randomly is roughly 1.2%. The December Earth encounter adds another layer of improbability. The 170 million mile approach distance places 3I, Atlas, at the optimal range for detailed observation with space-based telescopes while avoiding any gravitational perturbation of Earth's orbit. The timing coincides with optimal viewing geometry for Northern Hemisphere observatories. These combined constraints have a random probability of approximately 0.4%. The Jupiter encounter represents the most geometrically complex and statistically improbable aspect of the entire trajectory. The 3 million mile approach distance places 3I, Atlas, deep within Jupiter's magnetosphere, where charged particles and magnetic fields could interact with any artificial systems aboard the object. The encounter timing occurs when Jupiter is positioned for optimal observation from Earth-based telescopes. The probability of this encounter occurring randomly is estimated at less than 0.1%. When all trajectory constraints are considered simultaneously, Jackson's analysis yields a cumulative probability of approximately 0.005%, roughly one chance in 20,000. This statistical significance reaches levels that, in other fields of science, would be considered strong evidence for non-random phenomena. However, statistical analysis of rare events requires careful consideration of selection effects and observational biases that might artificially inflate the apparent improbability of observed phenomena. Dr. Sarah Greenstreet of the University of Washington has led efforts to understand these bias effects in the context of interstellar object detection and analysis. Greenstreet points out that our detection methods naturally favor interstellar objects with trajectories that bring them close to Earth and other planets. Objects passing through the outer solar system without planetary encounters are far less likely to be detected and studied, creating an observational bias toward apparently interesting trajectories. This selection effect might make precisely choreographed paths seem more common than they actually are. Additionally, the human tendency to find patterns in random data, known as apophenia, might influence interpretation of trajectory statistics. When presented with any specific sequence of events, it's possible to calculate extremely low probabilities by focusing on precise details while ignoring the vast number of alternative outcomes that would have seemed equally remarkable if they had occurred instead. The question of intentionality versus coincidence also depends on assumptions about the motivations and capabilities of hypothetical artificial intelligence. If 3I, Atlas, represents technology created by an advanced civilization, what objectives might such a trajectory serve? Several possibilities emerge from analysis of the path's characteristics. A reconnaissance mission designed to study our solar system's major planets would benefit enormously from the specific sequence of encounters exhibited by 3I, Atlas. The Mars flyby provides close-range observation of a terrestrial planet with atmospheric and surface features that could indicate habitability. The solar perihelion allows for detailed study of our star's characteristics and collection of solar wind samples. The Earth encounter enables comprehensive observation of our planet's atmosphere, magnetic field, and potential signs of technological civilization. The Jupiter flyby provides access to the solar system's largest planetary magnetosphere and its complex system of moons. Each encounter also occurs at optimal timing for scientific observation. The Mars flyby happens during dawn conditions that maximize atmospheric visibility. The solar perihelion timing coincides with a period when the object is hidden from Earth-based observation, potentially allowing for covert operations. The Earth encounter occurs during optimal viewing geometry for detailed surface observation. The Jupiter flyby takes place when the giant planet is well positioned for Earth-based monitoring of the encounter. An alternative interpretation suggests that the trajectory might be designed for efficient sampling of solar system material rather than planetary observation. As 3I, Atlas moves through different regions of interplanetary space. It encounters varying densities of dust, charged particles, and magnetic fields that could provide comprehensive information about our star system's properties. The retrograde orbit maximizes the object's relative velocity through this material, potentially enhancing collection efficiency. The gravitational mechanics of the trajectory also demonstrate sophisticated understanding of orbital dynamics if the path is indeed artificial. Each planetary encounter slightly modifies the object's trajectory through gravitational interaction, fine-tuning its path for subsequent encounters. This gravitational billiards effect requires precise initial conditions and sophisticated trajectory planning to execute successfully. Critics of intentional design hypotheses argue that the statistical analysis may be flawed by inadequate consideration of the vast number of possible trajectories that interstellar objects might follow. With billions of potential paths through three-dimensional space and countless possible timing relationships, even extremely improbable events must occasionally occur. The apparent significance of 3I, Atlas's trajectory, might result from the human tendency to assign special meaning to whatever unusual configuration happens to be observed. Furthermore, the assumption that artificial objects would necessarily follow optimal trajectories may be incorrect. Advanced civilizations might have priorities, constraints, or decision-making processes that differ dramatically from human expectations. What appears optimal from a human perspective might be irrelevant or counterproductive for genuinely alien intelligence. The debate over statistical significance versus coincidence reflects broader challenges in distinguishing between natural and artificial phenomena when dealing with objects that might represent technology far beyond human capabilities. Traditional SETI approaches focus on detecting obvious artificial signals like radio transmissions or laser pulses. However, truly advanced civilizations might employ reconnaissance methods so sophisticated that they're virtually indistinguishable from natural phenomena. This possibility raises the question of what evidence would constitute definitive proof of artificial origin for an object like 3I, Atlas. Statistical improbabilities, while suggestive, are insufficient on their own. Direct observation of artificial materials, geometric structures, or active systems would provide more compelling evidence. However, technology sufficiently advanced to construct interstellar probes might also be sophisticated enough to conceal such obvious signatures. The resolution of questions about 3I, Atlas's trajectory, will ultimately depend on continued observation as the object follows its predicted path. If the object deviates from gravitational predictions through course corrections or other anomalous behavior, such deviations would provide strong evidence for artificial systems. Conversely, if the trajectory precisely follows gravitational mechanics without any unexplained variations, natural origins would become more likely despite the statistical improbabilities. The statistical analysis of 3I, Atlas's trajectory, represents a new frontier in the search for extraterrestrial intelligence, one that focuses on subtle signatures rather than obvious signals. Whether this approach reveals genuine evidence of alien visitation or simply demonstrates the human capacity to find patterns in random events, it has already transformed our understanding of what constitutes meaningful data in the cosmic search for our neighbors among the stars. The 3I Atlas phenomenon has forced the SETI community to confront fundamental assumptions about how extraterrestrial intelligence might manifest in our cosmic neighborhood. For over 6 decades, SETI research has predominantly focused on detecting radio signals, optical pulses, and other obvious artificial transmissions from distant civilizations. The possibility that alien intelligence might visit our solar system in the form of sophisticated reconnaissance probes represents a paradigm shift that could reshape the entire field. Dr. Jill Tarter, former director of the SETI Institute and a pioneer in the search for extraterrestrial intelligence, acknowledges that 3I Atlas has opened our eyes to detection modalities we hadn't seriously considered. Traditional SETI approaches assume that advanced civilizations would want to announce their presence through detectable signals. However, a reconnaissance mission would likely prioritize stealth and discretion over communication, requiring entirely different detection strategies. The implications for SETI methodology are profound. If interstellar visitors like 3I Atlas represent a genuine phenomenon, then future search efforts must expand beyond electromagnetic signals to include systematic monitoring of unusual objects within our solar system. This shift requires new observational capabilities, analysis techniques, and theoretical frameworks for distinguishing between natural and artificial phenomena. The most immediate impact concerns the need for enhanced interstellar object detection and tracking systems. Current astronomical surveys, like the Catalina Sky Survey and Linear, were designed primarily to identify potentially hazardous asteroids rather than interstellar visitors. While these systems successfully detected both Oumuamua and 3I Atlas, they lack the sensitivity and coverage necessary for comprehensive monitoring of interstellar traffic. Dr. Robert Werrick of the Institute for Astronomy at the University of Hawaii, who led the team that discovered Oumuamua, advocates for dedicated interstellar object survey programs. These specialized systems would employ wide-field telescopes with advanced image processing algorithms specifically designed to identify objects with hyperbolic trajectories and unusual characteristics. The goal would be early detection of interstellar visitors while they're still in the outer solar system, allowing for extended observation periods and potential spacecraft intercept missions. The Vera Rubin Observatory, scheduled to begin operations in 2024, represents a significant step toward comprehensive sky monitoring. Its large synoptic survey telescope will photograph the entire visible sky every few nights, creating an unprecedented database of astronomical observations. This systematic approach should dramatically improve our ability to detect and characterize interstellar objects, potentially revealing whether visitors like 3I Atlas are rare anomalies or representatives of regular interstellar traffic. However, enhanced detection capabilities raise complex questions about data interpretation and scientific standards. The SETI community has long grappled with the balance between open scientific inquiry and responsible speculation. Claims of potential extraterrestrial contact carry enormous implications for humanity and require extraordinary evidence to support extraordinary conclusions. The 3I Atlas case illustrates this challenge perfectly. While statistical analysis suggests improbable trajectory characteristics, the evidence remains circumstantial and subject to alternative explanations. Publishing speculative interpretations risks undermining SETI's scientific credibility, while excessive caution might cause researchers to overlook genuine evidence of extraterrestrial visitation. Dr. Seth Shostak of the SETI Institute argues for transparent reporting of unusual observations while maintaining rigorous analytical standards. The scientific method depends on open discussion of data and interpretations, he explains. Our responsibility is to present evidence objectively while clearly distinguishing between observations and speculations about their implications. This approach requires new protocols for investigating potentially artificial objects. The SETI community has developed extensive guidelines for verifying and reporting electromagnetic signals, including requirements for independent confirmation and peer review before public announcement. Similar standards must be established for physical objects that might represent extraterrestrial technology. The International Astronomical Union has begun developing frameworks for interstellar object classification and investigation procedures. These protocols emphasize systematic observation, statistical analysis, and collaborative research approaches that minimize the influence of individual bias or wishful thinking. The goal is establishing objective criteria for distinguishing between natural phenomena and genuinely anomalous objects that might warrant extraordinary claims. Beyond detection and analysis challenges, 3I, Atlas raises profound questions about human preparedness for potential contact with extraterrestrial intelligence. If reconnaissance probes are indeed visiting our solar system, they represent a form of contact that differs dramatically from the distant radio signals that SETI has long anticipated. The psychological and sociological implications of nearby alien surveillance could prove far more challenging than receiving messages from distant civilizations. Radio signals from thousands of light years away pose no immediate threat and allow humanity time to process the implications of contact. Physical objects within our solar system suggest active interest in human civilization and raise immediate questions about alien intentions and capabilities. Dr. Douglas Vakoch, president of METI International, emphasizes the need for serious consideration of contact scenarios involving visiting spacecraft. We've spent decades preparing for the possibility of receiving radio messages from distant stars, he notes. We're far less prepared for the possibility that advanced civilizations might be studying us directly through reconnaissance missions. This preparedness gap extends to governmental and institutional responses. While protocols exist for handling potential SETI detections, they assume contact through electromagnetic signals rather than physical visitation. The 3I, Atlas phenomenon, highlights the need for comprehensive frameworks addressing all possible manifestations of extraterrestrial intelligence, including scenarios that might require immediate rather than contemplative responses. The implications for space exploration policy are equally significant. If interstellar visitors are indeed present in our solar system, future space missions might encounter artificial objects or evidence of extraterrestrial activity. Space agencies must consider these possibilities when designing exploration programs and developing contingency protocols for unexpected discoveries. NASA's Planetary Defense Coordination Office, established to track potentially hazardous asteroids, has begun incorporating interstellar object monitoring into its mission scope. This expansion reflects growing recognition that unusual visitors like 3I, Atlas, warrant careful tracking regardless of their ultimate origin. The office's dual focus on natural hazards and potentially artificial objects represents an important evolution in space surveillance priorities. The confirmation of artificial origin for an object like 3I, Atlas, would represent the most significant discovery in human history, fundamentally altering our understanding of our place in the universe. Such confirmation would prove that advanced civilizations exist possess interstellar travel capabilities, and consider our solar system worthy of investigation. The implications would extend far beyond astronomy to encompass philosophy, religion, politics, and every aspect of human culture. However, the threshold for such confirmation must remain extraordinarily high. The history of science includes numerous examples of initially promising anomalies that ultimately received conventional explanations. The canals of Mars, pulsars initially dubbed little green men, and various purported biosignatures have all demonstrated the danger of premature conclusions about extraterrestrial phenomena. The 3I Atlas case may ultimately prove to be another example of human pattern-seeking behavior, identifying artificial meaning in natural randomness. The object's trajectory, while statistically improbable, might simply represent an extraordinary coincidence rather than evidence of design. Only continued observation and analysis can resolve these questions definitively. Yet, even if 3I Atlas proves to be entirely natural, its impact on SETI methodology and thinking will remain profound. The object has demonstrated that interstellar visitors are detectable with current technology, and that subtle signatures of artificial origin can be identified through careful statistical analysis. These lessons will inform future searches regardless of 3I Atlas's ultimate nature. The case has also highlighted the importance of interdisciplinary collaboration in SETI research. Understanding objects like 3I Atlas requires expertise in orbital mechanics, statistical analysis, materials science, and numerous other fields beyond traditional radio astronomy. This collaborative approach may prove essential for recognizing and interpreting genuinely artificial phenomena when they finally reveal themselves. 3I Atlas represents either humanity's most profound discovery or its most elaborate cosmic coincidence. This 7-mile-wide visitor from interstellar space exhibits all the hallmarks that the black forest theory would predict: a carefully choreographed trajectory with 1 in 2,000 odds, pristine composition suggesting ancient origins, and a sequence of planetary flybys that reads like a reconnaissance mission playbook. Yet for all its anomalies, the missing cometary gases, the statistically improbable path, the strategic timing of its hidden perihelion 3I Atlas stops just short of providing the definitive proof that would confirm we are not alone. As it completes its grand tour of our solar system and departs into the cosmic dark, this enigmatic object leaves us with the most tantalizing question in human history. Are we witnessing first contact through the black forest's silent watchers, or simply the universe's most remarkable coincidence?